Hello, today we're continuing in the A-Level Physics Revision series looking at elementary particles and the Standard Model. So far we've established that an atom has a central nucleus which consists of protons and neutrons, and it has orbiting electrons. But those electrons don't strictly orbit, because if they did they would spiral into the nucleus. They are actually waves, so they orbit in wave fashion, and as we showed in the video on atomic structure and electron energy levels, the electrons can only occupy certain energy levels, and that's the reason they cannot spiral in. They can only occupy certain energy levels, and that precludes them from moving in and colliding with the nucleus. We shall see in a later video that the protons in the nucleus are held together by what's called the strong nuclear force. If they were not held together, then the positively charged protons would repel one another and the whole nucleus would self-destruct. The question is, are the protons and the neutrons and the electrons the most basic form of particles? Well, as far as we know, there is nothing smaller than an electron. We cannot subdivide an electron. But we now know that protons and neutrons are made up of quarks. A proton has 2 up quarks and 1 down quark, and a neutron has 1 up quark and 2 down quarks. Quarks were essentially discovered by a man called Murray Gell-Mann in 1961. He was the one who had the opportunity to name them. And they look as though they ought to be pronounced quark, and I don't think there's anything wrong in calling them quarks. He wanted to call them quarks, so conventionally that's what we do. The name comes from James Joyce's Finnegan's Wake, where the line goes, 3 quarks for Muster Mark, sure he has not got much of a bark, and sure any he has, it's all beside the mark. Now that would suggest that since we're rhyming with bark and mark, it ought to be a quark. But Gell-Mann was very clear, he wanted it to be called a quark, so strictly that's what we ought to call it. And quarks are, as far as protons and neutrons are concerned, the basic units that we're aware of. And scientists have now compiled what is called the Standard Model, and I'll construct it for you. You don't need to know all of these things, but you do need to know most. So I'll show you the Standard Model in its entirety and then explain the bits that you don't yet need to know about. We normally draw the Standard Model as a 4x4 grid. There are in fact 6 quarks. There are the up quark and the down quark, which is what we've got here. And then there are essentially heavier versions of these quarks. There's a charm quark and a strange quark, and there's a top quark and there's a bottom quark. And those are the 6 quarks, the 6 fundamental particles. And those are the quarks. Then the bottom part of the table is for what's called the leptons. Now, the most well-known lepton is an electron. But just like the quarks, there are 2 versions that are heavier than an electron. They're heavy electrons. One is called the muon, and one is called the tau. And each of these 3 particles has what's called a corresponding neutrino. So there's the electron neutrino, there's the muon neutrino, and there's the tau neutrino. So we've got 6 quarks and 6 leptons. We've got basic quarks, the up and down, and then 4 heavier versions. We've got the basic leptons, the electron and the electron neutrino, and 4 heavier versions. What are these for? Oh, and these are all particles. What are these 4 boxes for? Well, they're for what are called gauge bosons. There's the photon, there's the gluon. The gluon is, as we shall see later, responsible for holding the nucleus together. It's basically the exchange particle responsible for the strong nuclear force. There's the W plus and minus boson and the Z boson, sometimes called the Z boson, and those two are, or those three strictly, W plus and minus and Z, are responsible for the weak interaction, which we shall come on to shortly. And those particles and bosons are what we now understand to be the elementary forms of nature. Nothing smaller, or there's nothing that you can get by dividing these. We can't divide these. There's nothing smaller than those. Now it turns out that for every particle there is what's called an antiparticle. Antiparticles are exactly the same as particles. Every single characteristic is the same except one. They always have the opposite charge. So for example, a proton has a charge of +1. An antiproton, which is usually a proton with a bar, has a charge of -1. Matter and antimatter are created from energy. Energy produces matter plus antimatter, and it does so through the famous equation E equals mc². If you have energy, you can create mass. But here is the point. If you've got, let's say, energy, which we represent in the form of photons, they might give off matter and antimatter, but they should give off in exactly the same amounts, exactly the same mass. Antimatter does not have negative mass. It has positive mass, but opposite charge. And there should be exactly the same amount of matter and antimatter. And when matter and antimatter come together, they annihilate to produce energy again. So energy produces the matter and the antimatter. When matter and antimatter come together, they annihilate. So one of the big puzzles of the universe is that if right at the beginning energy gave rise to the production of matter and antimatter, why isn't it that all the matter and the antimatter hasn't simply since collided and produced energy again? Why is there still what seems to be in the universe a surplus of matter? Let's look in more detail at these quarks. The quarks you need to know about are the up, the down and the strange. So in the standard model you don't need to know about the charm, the top or the bottom. But you do need to know pretty much about everything else. So we're going to look at the up, the down and the strange quarks. We're going to look at their charge. We're going to look at what's called the baryon number, and we're going to look at their strangeness. The charge of an up quark is 2/3. The charge of a down quark is 1/3, and the charge of a strange quark is -1/3. A baryon number of an up quark is 1/3, a baryon number of a down quark is 1/3, and the baryon number of a strange quark is 1/3. The strangeness of an up quark is 0, the strangeness of a down quark is 0, and the strangeness of a strange quark by a peculiar notion is -1. Now let's look at, these were all quarks. Now let's look at antiquarks, because all matter has antimatter. And again we're going to look at charge, baryon number and strangeness. Well, the charge is always the opposite of matter. So for an up quark, the anti-up quark is -2/3. The down quark has, oh, I made a mistake here, that should be -1/3. I hope I've already pointed that out in the text on the video before we got here. Big mistake, that's -1/3 as a charge for the down quark. So the anti-down quark has the opposite of this, which is +1/3. The anti-strange quark has the opposite of -1/3, which is +1/3. The baryon numbers are -1/3, opposite of that, -1/3, opposite of that, -1/3, opposite of that. And the strangeness is 0 and 0, and now the opposite of -1, +1. So these are the charge baryon numbers and strange numbers of the anti-quarks. So let's use that information to think about a proton. I told you that a proton was 2 up quarks and a down quark. So what does a proton mean in terms of charge? Well, a proton will have two lots of up quarks, so it will have 4/3, and a down quark, which is -1/3. And that gives a total charge of +1, which is exactly what you expect a proton to be. A neutron, on the other hand, has one up quark and two down quarks, which means it has a charge of +2/3 minus two lots of 1/3, so it's 2/3 minus 2/3, which means a neutron has, as expected, a charge of 0. What is the baryon number of a proton? It is two lots of up quarks, one lot of down quark, so it's two of those and one of those, 2/3 plus 1/3. The baryon number equals 1 for a proton. What about a neutron? Well, a neutron is one up quark, two down quarks, one of those plus two of those, 1/3 plus 2/3 is 1. So the baryon number for a neutron is also 1. If you do the same thing for an antiproton, you will see that an antiproton that has two anti-up quarks and one anti-down quark will have a charge of two lots of -2/3, that's -4/3, plus 1/3 is equal to -1. So an antiproton has a charge of -1, whereas a proton has a charge of +1. We've used the word baryon. Now we need to establish what on earth that is. Everything in the world is divided into two types of things. It is either what's called a fermion, which basically means it's matter, or it's a boson, which means that it's got something to do with, certainly at the elementary level, we come here, it is these gauge bosons here. Now fermions are divided into two quite distinct types. One is called hadrons, and the other is called leptons. Leptons, remember, were the electrons and the neutrinos. They, incidentally, do not feel the strong nuclear force, but hadrons do. Hadrons are themselves divided into two categories of particles. There are the baryons, which is the word we've been using, and obviously those include protons and neutrons, and also mesons. What are mesons? Well, mesons you can have, as we shall show in a moment, pi mesons, k mesons, and some other mesons which you don't need to know about for A level. Mesons consist of a quark and an antiquark pair. So, for example, you can produce a complete table. You can have what's called a pi 0, which is an up, or down, anti-down. So up, anti-up, or down, anti-down is a pi 0. A pi plus has an up, anti-down. And a pi minus has a down, anti-up quark. Then there are K mesons. The K anti-0 is a strange anti-down. The K minus is a strange up. The K plus is an up anti-strange, and the K 0 is down anti-strange. In each case, you'll see that these particles are made of one ordinary quark and one antiquark. And if you go back to the table that we just constructed and look at the relative charges on an up quark and a down quark, or an up quark and an anti-down quark, add those two together, you will find that you will get either a positive charge or a negative charge or a neutral charge because of the arrangement of these quarks. Now, there is no such thing as a free quark. You cannot get a quark out of either a meson, where it is in a pair, or things like protons and neutrons, where they exist in triplets. And the reason is this. Let's take a proton, which has 2 up quarks and 1 down quark. And let's say that we try to get one of those quarks out. So we distort the proton so that it has an up quark and a down quark and another up quark. And the plan is to try and separate off that quark so that it is isolated. What will actually happening is, in order to do that, you have to give that proton a huge amount of energy. And if you give it a huge amount of energy, what happens is that here's the up quark, here's the down quark, here's the up quark you're trying to release. That energy will lead to pair production. And what you will get is a quark-anti-quark pair produced because of all the energy. It's called pair production. And then all that happens is that this up quark goes back into here, and that anti-quark goes there, and you end up with a proton, which is what you started with, plus an up, anti-up meson. But you never get an individual quark coming out, because the amount of energy you'd need to put in order to release that quark will mean that you always get pair production first, and that pair production simply produces either something like a proton and a meson. You'll see, incidentally, that this up, anti-up meson is, of course, a pi 0. Up, anti-up is a pi 0. Finally, I want to look at the weak interaction. We shall learn more about the 4 fundamental forces in a later video, but one of them is the weak interaction. And what the weak interaction basically does is it takes an up quark and it turns it into a down quark, or vice versa. Let's take, for example, the situation where a neutron decays into a proton. When it does so, it also produces an electron plus what's called an anti-electron neutrino. These two, the electron and the anti-electron neutrino, are leptons. They don't have quarks. Only these two have quarks. And what is it? Well, a neutron is an up, 2 down, and that becomes 2 ups and a down, plus the electron, plus the antineutrino. What has happened? That quark, which was a down quark, has been converted to an up quark. And that is what the weak interaction does. If you look at the heart of the sun, what is going on in the sun is that protons are being converted into neutrons, plus positrons, which are the antiparticles for electrons, plus ordinary electron neutrinos. What is a proton? 2 ups and a down quark. That produces 1 up and 2 downs, that's the neutron, plus the positron, plus the electron neutrino. Once again, it is that middle quark, the up quark, which is changed into a down quark, and that is done via the weak interaction. Whenever you do these interactions, certain things are conserved. The overall charge must always be conserved. The overall baryon number must always be conserved, and the overall strangeness must also be conserved. When you're talking about leptons, there are further rules that for each of the 3 categories of the electrons, or the leptons, remember we had the electron, the muon and the tau, and for the neutrinos there was the electron neutrino, the mu neutrino and the tau neutrino. For each of those separately, their values must be conserved. So you cannot have an electron giving rise to a mu neutrino, as it's all beside the mark. Now that would suggest that since we're rhyming with bark and mark, it ought to be a quark. But Gell-Mann was very clear. He wanted it to be called a quark. So strictly that's what we ought to call it. And quarks are, as far as protons and neutrons are concerned, the basic units that we're aware of. And scientists have now compiled what is called the Standard Model, and I'll construct it for you. You don't need to know all of these things, but you do need to. Quarks were essentially discovered by a man called Murray Gell-Mann in 1961. He was the one who had the opportunity to name them. And they look as though they ought to be pronounced quark, and I don't think there's anything wrong in calling them quarks. He wanted to call them quarks, so conventionally that's what we do. The name comes from James Joyce's Finnegan's Wake, where the line goes, 3 quarks for Muster Mark, sure he has not got much of a bark, and sure any he had. Hello, today we're continuing in the A-Level Physics Revision series looking at elementary particles and the Standard Model. So far we've established that an atom has a central nucleus which consists of protons and neutrons, and it has orbiting electrons. But those electrons don't strictly orbit, because if they did they would spiral into the nucleus. They are actually waves, so they orbit in wave fashion, and the whole nucleus would self-destruct. The question is, are the protons and the neutrons and the electrons the most basic form of particles? Well, as far as we know, there is nothing smaller than an electron. We cannot subdivide an electron. But we now know that protons and neutrons are made up of quarks. A proton has 2 up quarks and 1 down quark, and a neutron has 1 up quark and 2 down quarks. Showed in the video on atomic structure and electron energy levels, the electrons can only occupy certain energy levels, and that's the reason they cannot spiral in. They can only occupy certain energy levels, and that precludes them from moving in and colliding with the nucleus. We shall see in a later video that the protons in the nucleus are held together by what's called the strong nuclear force. If they were not held together, then the positively charged protons would repel one another